be able to get. Now if you look at this, nature in terms of sustainable development, the nature's way is this. Basically the solar energy, you have 4 or 5 different things which are sort of working in harmony with each other. Because you have, for example, the solar energy, which is the spectrum which is absorbed. Then there are these natural processes, the photosynthesis processes, and all those kinds of things. And the nature remains very sustainable, quiet, and clean in this particular way. But we have sort of done something different in terms of our energy structure. Remember, all these things require energy and energy transformation. But nature is not in a hurry as human being is. Okay? And that is where this power and speed issues come into play. As I will just indicate to you. Like for example, this is nature's way of doing things. If you consider solar cells, like these leaves here, which convert the solar energy into some storage, here they are low efficiency, and in fact they are expendable. The leaves fall down after they sort of generate the food, and they give to this particular tree. This tree is more like a storage, more like a battery, which is robust and reproducible, and that is why we get a clean environment, no pollution. This is a sustainable way of energy development. On the other hand, if you in fact, this particular aspect of sustainability, I just want to show you this quote in the Science magazine in 1912. The scientist Sian, he said, inside of these will take place the photochemical processes that hitherto have been guarded secrets of plants, but that will have to be mastered by human industry, which will know how to make them bear even more abundant fruit than nature, for nature is not in a hurry and mankind is. It's a very interesting quote which says that in terms of progress or development, we are looking at energy, but we have not looked at how to use the nature's processes, to make them more efficient, which will still keep them clean and green, and at the same time, which can get a lot of power rather than energy, meaning we will get energy at a faster rate. This is very interesting, and if you look at what we have been doing mostly in the last 50 years, a lot of things with silicon. Okay, or such materials and big gadgets and so on. So this is something not what nature is doing. Okay, this is what we have been doing. And our entire dependence on silicon has been very substantial. It is very interesting that if you take computer chips, integrated circuit chips, and anything, memory or solar cell or anything, we are doing everything on silicon. And there is of course some reason for that, because the silicon technology matured sufficiently in advance, and therefore the technologists say it is very interesting to show you the periodic table. What is seen is, for technologists, there are so many elements, 117 elements around here, but for technologists it is silicon everywhere. They look at silicon, very silicon. Can I do something on silicon and so on? So our dependence on silicon is rather substantial, and the question is, are we limited in our imagination? And remember, in nature's processes of energy or even memory, there is no silicon in our brain, for example, but we still remember a few things. But our entire dependence on something is on silicon, and there is now a current drive to see whether we can use some other interesting earth-abundant elements to harness energy, because silicon will have too much competition from the types of sectors that we have, and it is very important to try to look at this. One of the reasons why silicon is important is silicon is abundant in Earth's crust, but there are other elements like iron, and there is titanium and so on, which are substantially available, and people are trying to see if we can make use of some of these elements for some innovative studies. Now, the other interesting thing is, now during the last 20-30 years, what has happened is, if you consider organic compounds, inorganic compounds, and carbon family of compounds, we have enormous options of putting them together. So, in a sense, in the last 20 to 30 years, the progress has been such that material science has matured in a way that we are able to manipulate and put together materials in very interesting ways, interesting combinations, hybrids, and so on, so to be able to generate responses of properties which will be very useful in diverse set of applications, and that has added strength to the types of experiments that we have been doing. Another interesting thing is the emergence of nanoscience in the last 10 to 20 years. What is interesting to see is that because of the quantum phenomena, as well as the large surface to volume ratio, which allows us to manipulate the surface substantially, we are able to generate fantastic set of properties of materials. If you look at it, for example, if you look at gold nanoparticles, you have so many optically different gold materials that you are able to develop. Gold is not the traditional yellow, but gold can be violet, gold can be green, gold can be blue, because of the nature of electronic states that we harness into nanosystems and so on. If you look at carbon, for example, the carbon is the barbecue carbon or coal, which is black for most people, but when you make it nano, and interestingly, not only nano, but if you passivate them by different molecules, small molecules, organic molecules, you can make carbon blue, green, red, and so on. What it means for a material scientist like me is that this is a single element in the periodic table here, but now I'm able to sort of modify its property and generate for myself, for manipulation, a range of materials with different electronic properties. Similarly here, that means for a material scientist, this periodic table has actually exploded with opportunities. And it is very important to try to use them in the energy context, which is what many people are trying to do. Now, coming to the topic of this conference, Mossbauer spectroscopy in energy and environment applications, it is very interesting that basically Fe and tin-based oxides, which can be mostly harnessed by common Mossbauer spectroscopy sources and so on, these types of oxides are used in so many applications, different applications which relate to energy and environment. But as I see, since I had done some Mossbauer spectroscopy in collaboration with Professor Hammerly here and others, but I have seen that in the last 5 to 10 years, in terms of number of papers, where Mossbauer spectroscopy could actually contribute much more than which is able to do now in terms of details, and there is a lot of opportunity here to actually use Fe and tin-based Mossbauer spectroscopy for a number of applications like this. And I think this particular sector will grow, where the people who are doing energy will communicate more with Mossbauer, because the ability of Mossbauer to generate atomistic information and hyperfine interaction details is absolutely unique. And I think the level of science that one is entering now in energy and environment will need the intervention of a technique like Mossbauer spectroscopy in much finer details than some gross effect that people have been talking about. I will just skip through, just run through a few slides where you can see, for example, there have been dye-sensitized solar cells based on tin oxide. You can look at the morphologies that people are generating, which are, there are electrolyte, zinc oxide, tin oxide materials put together. And I think Mossbauer spectroscopy can, and they are trying to make flexible solar cells like this. So this is where, for example, Mossbauer spectroscopy can be very valuable in defining the interfaces, defects, and so on. I will breeze through some slides. For example, look at this. This is a SNO2. This is by one of our collaborators, Henry Smith, who has done SNO2-based dye-sensitized hybrid solar cells. And a number of things happen in these kinds of complex solar cells, where you have a material like tin oxide, then there are molecules, dyes which are attached to it, there are surface defect, oxygen vacancies, and so on. And I'm sure Mossbauer spectroscopy, we have been doing some, but I think there is much to contribute here by this technique. You look at this. This is Fe3O4 nano sheets on one-dimensional carbon nanofibers, and this is for supercapacitor application. So this is an example again where some people have been using Mossbauer spectroscopy, but I think much more is needed. I will just give you a few examples before I begin to show some of my work. This is tin oxide. Now a material tin oxide with MNO coating on the top, and this is again a capacitative behavior. And look at the interface quality here, and people are trying to see if there are interdiffusion reactions and so on. And once again, from my point of view, Mossbauer, in some of this work, Mossbauer has not been used. In some, of course, it has been used, but I think there is ample opportunity for a really insightful study that can be done with Mossbauer spectroscopy. Like, there are certain examples where this is like iron-doped barium titanate, and in this case, Mossbauer spectroscopy has been used to try to understand what is the state of iron, how in the photochemical response and iron doping can lead to surface electronic states which can influence substantial increase in the photoelectrochemical activity and so on. If you look at this one, for example, this is again Fe2O3, this is Gratzel's paper, on which the nanostructures which are done in a very diverse way, basically with the Fe2O3 phase, lead to substantial changes in photoelectrochemical splitting and so on. I'm giving these examples because these are, for me, a learning exercise in a sense that these are the iron and tin-based materials which people have not looked at with great seriousness with Mossbauer spectroscopy, but obviously a lot of insight can be provided. There are situations where water purification, which is an environmental issue, is also there. Is, for example, two metal electrodes here which are used for electrocoagulation, and they show how under different circumstances Mossbauer spectroscopy can throw some light onto the types of things going on the surfaces. Let me come to some of our work in this particular area. Just to indicate something that we have been doing is this dye sensitized solar cell application and quantum dot sensitized solar cell application. Now in this particular scenario, what people do is you have an oxide layer, oxide here, which is like a porous layer. So you take a TiO2 or SnO2 or zinc oxide powder or some zinc stannate or some powder, and you make a porous film. Now in that porous film, you infiltrate dye molecules like these dots here. These are dye molecules, okay? Or you can have quantum dots infiltrated there. And then you have two electrodes. There is some electrolyte here, and when the dye molecule, these dye molecules absorb the photon, the electron is given to TiO2, and this is an express highway. It connects to the one electrode, and then the whole is carried by the electrolyte to the other electrode. So this is a kind of a principle of this particular solar cell, and as you will see,